Good afternoon or good evening, depending on where you are. My name is Joaquin Moris. I'm a PhD student and I work with Dr. Andrew Kennedy and Dr. Johannes Westering at the University of Notre Dame. And today I'm going to talk to you about wave run-up load reduction inside a building array. Wave load reduction inside a building array or on sheltered buildings has been seen in the past. For instance, after Hurricane Sandy, two regions were identified in Ortley Beach, New Jersey. Region A and Region B. In Region A, there were no large buildings providing shelter. And in Region B, there were 3 large buildings providing shelter. And as you can see in the figure, in Region A, there were way more buildings that experienced failure of their foundations. And in Region B, most of the buildings survived. So we can expect that if we have some sheltering, we're going to experience less damage in the structures. And if we don't have sheltering, we're going to experience more damage. Also, after field observation of the 2004 Indian Ocean tsunami, 2006 Java tsunami, and the 2009 South Pacific tsunami, it was seen that if there is some sheltering provided by surrounding structures or buildings, the damage is going to be reduced as well. So our current situation is that wave run-up loads in current standards and model, they don't consider this urban development or sheltering on buildings. They assume a better condition, meaning that there are no buildings placed in the domain when you are computing the loads. For instance, the American standard, they compute the loads with a value proportional to the momentum flux, but the loads in building number 1, building number 2, and building number 3, they are computed, they are assumed that they are the same. Same as for the Japanese standard. For instance, building number 2, it has some shelter provided by building number 1, and building number 3 has some shelter providing by building number 1 or 2. And this is not accounted in the standards. What we proposed is to investigate how wave loading is reduced on these shelter buildings by analyzing wave loading laboratory tests, extending the laboratory test with numerical models, and finding some way to consider the effect of sheltering on wave loading calculations. So the load on the building number 1, which is unobstructed, the load can be estimated from standards, but the load in building number 2 and in building number 3, they are influenced by the presence of the building number 1, and we want to account for that. We conducted experiments in the directional wave basin in Oregon State University between January and May of last year, and this was a collaborative project among several universities: Notre Dame, University of Notre Dame, University of Southern California, Oregon State University, Kyoto University, and the US Naval Academy. The experimental setup consisted in a 10 by 10 building array of a total of 100 idealized structures. The structures were placed in the test section representing a coastal developed region. On the left, you have the wave maker. The waves traveled from the left to the right over a 120 slope until they reach a 1 meter elevated flat section. In this figure, you can see the wave maker in the back. The waves traveled from the back to the front, as you can see in the arrow. And here you can see the 10 by 10 building array, but I would like to focus our attention on these 5 buildings that are highlighted in yellow. They were instrumented with inline load zones. We measured the wave loading in these 5 boxes. Here's another figure with the waves coming from the bottom. And here are the 5 inline load cells where the loads were recorded. We also instrumented the slope with wave gauges and the test section with ultrasonic wave gauges and ADVs, and also the inline load cells here in red. We tested 7 different wave conditions, 3 solitary waves, and 4 error function waves. Error function waves are similar to solitary waves, but their effective wavelength is larger and they don't have a permanent shape. We conducted each wave twice, so in total we had 14 waves. And the still water level was set up to 98 centimeters, meaning 2 centimeters below the test section level. In the video on the top, there's an example of a wave hitting the building array. It's a breaking wave condition, an error function, which is represented in the right in the plots in blue. In the first figure, you can see the loads on the first row, and as you go downwards, you see the loads that are reduced because the last plot corresponds to the load in the 5th row. In the other video, we can see a non-breaking wave condition, and it's represented by the line in red. And as you can see, the magnitude of the load is less than the breaking condition, but it is reduced as you go further inland. We wanted to extend the laboratory experiment with numerical simulations because to account for the effect of the building array on the run-up loads, we need wave loading in the building with the building array providing shelter, and we need the wave loading without the building array providing shelter to compare the loads. We are going to call this second type of loads unobstructed loads. And in lab, the building array was very difficult to modify, but computationally, this is very simple. And also we can compute the loads in all rows. We chose olaFlow numerical model because it's based on the Navier-Stokes equation, so we can solve the flow in 3D. It solves air and water. It provides easy generation and absorption features at the boundary, and it includes all the major turbulence models. And it has been used in the past to compute loads in coastal structures. So our numerical domain had to be reduced instead of 10-meter width to a 3-meter width domain because it was computationally too expensive for our computer resources. With an unstructured mesh, the resolution was increased in key areas. For instance, in the surrounding of the buildings, we placed most of the resolution because we really wanted to solve the flow there and capture the loads as accurate as possible. We tested different meshes. In this presentation, I'm going to show you the results using the finest mesh. And something to keep in mind, each simulation took about 10 days with our computer resources. They were very expensive simulations. The model performance in this figure can be seen visually. These are snapshots of the breaking wave condition. You can see that the model captures pretty well what happened in the laboratory. Here you can see the water rising up on the front of the first row. Also, the front of the bore is well captured by the model. The splashing apparently is well captured. Even some overtopping on the first row was well captured by the model. The agreement on the offshore wave gauges was reasonable between the model and the data. The agreement with the ultrasonic wave gauges in the test section was also well captured by the model. Was reasonable, except in gauges 2 and 4 where there was a lot of water splashing. So maybe there the model was not able to capture the water elevation properly, but overall the agreement was pretty good. The velocities were also well captured by the model, and the loads were well captured by the model. You can see in this figure the time series of the load in row 1, 2, 3, 4, 5, and the magnitudes and the peaks were well captured by the numerical model. So in the numerical model, our strategy was to run a set of 10 simulations for each wave condition, the broken wave and the unbroken wave, by gradually removing the frontmost row of the buildings. This would give us the loads in all rows. For instance, if we remove row 1, we're going to get unobstructed loads in row 2. If we remove row 2, we're going to get the loads in row 3, and so on, until we only have one row left. After computing these simulations, we were able to compute a load reduction factor. It's a metric that we define as the maximum load in row L with n number of rows providing shelter divided by the unobstructed load at the same row location, but with no rows providing shelter. So this gives us how the load changes due to the presence of the building array. In the figure, you can see here an upper envelope of all the load reduction factors. We can draw some conclusions from here. First, the maximum wave loading decreases as the number of rows providing shelter increases. This is not surprising, but in addition, the rate of sheltering decreases as the number of rows providing shelter increases. This is given by the slope of the upper envelope. It's becoming flatter when a lot of rows are providing shelter. For 4 or more rows providing shelter, load reduction factor is about 0.2, meaning that after you pass the 4 first rows, loads are reduced about 4 to 5 times. And also for n greater than 4, there is not more significant reduction in the loads, meaning that most of the reduction occurs in the first 3 rows. We also wanted to check how the run-up changes in the cross-short streets, because the loads are reduced inside the building array, and that means that the energy must go somewhere. And if we check how the run-up changes when we compare it to the bare earth condition, meaning with no buildings in the test section, we see that the run-up can be as high as 2.6 times the bare earth condition. So we can conclude that there's a considerable increase in the maximum inundation level in the cross-shore streets. If we compare the velocity to a bare earth condition, we see that there's not a considerable increase, but there's still an increase up to about 1.2. And if we check the change in the momentum flux, comparing it with the bare earth condition, we see that the momentum flux can be increased up to 1.8 times bare earth condition. So we can conclude that there's a considerable increase in both the run-up and the momentum flux. And this could be very important. For instance, if we are designing and building for tsunami evacuation, a vertical evacuation, we must consider this because the run-up could be as high as 2.6 times more. I would like to acknowledge our funding sources, the NSF and NIST, and also would like to express our gratitude to all the people that help us in the lab experiments. Here are the references used in the presentation, and I would accept any questions while you can look at the main key points of the talk. Thank you.